This presentation is part of the TI-Nfocus AP Calculus video series. In this video, I'll discuss a specific concept associated with the 2017 AP Calculus exam, free response question BC6, namely alternating series. My name is Steve Kokoska. I'm a professor at Bloomsburg University in Pennsylvania, and I'm a former AP Calculus chief reader. Here's an outline of the information presented in this video. I'll begin with a definition of an alternating series, and then I'll consider a test for convergence or divergence, the alternating series test, and I'll also present a geometric interpretation of this test. Next, I'll consider how we estimate sums of a convergent alternating series and the alternating series error bound. And finally, I'll present a few examples and leave some of the solutions for you. As the name suggests, an alternating series is a series whose terms alternate between positive and negative terms. And here are a few examples. So the nth term of an alternating series can be written in one of these forms. Note that there are other forms also, but b sub n is a positive number. Here's the statement of the alternating series test. Given an alternating series, focus on the positive parts of the terms of the series, the b sub n's in the definition. If the series satisfies these two properties, that is, if the b's, the positive terms, are decreasing and the limit of the b's, the positive terms, is 0, then the series is convergent. Here's a geometric interpretation of a convergent alternating series. Suppose we compute and plot the partial sums on a number line. Since b sub n goes to 0 and the terms are decreasing, the successive quote-unquote steps become smaller and smaller. That means that the even partial sums are increasing and the odd partial sums are decreasing. So it seems reasonable, and the graph suggests, that both the even and the odd partial sums converge to some number s. Alright, well, let's see if we can use this test. In this example, determine whether this series converges or diverges. First, it is an alternating series. We need to make sure that that's true before checking the conditions for the alternating series test. The positive terms here are decreasing, and the limit of the positive terms is 0. Therefore, by the AST, the original series is convergent. Here's a graph to help with this conclusion. This shows a plot of the terms of the series in blue and the partial sums of the series in green. I think this graph shows how both the even and the odd partial sums converge to some number s. Here's another example. Let's determine whether this series converges or diverges. Well, first, it is an alternating series. But it isn't obvious, at least to me, that the sequence b sub n is decreasing. So I'll consider a related function, namely f of x equal to x times e to the minus x. I found the first derivative, and I can see that f is decreasing on the interval 1 to infinity. Can you see why? If x is greater than 1, then f prime of x is less than 0. This argument shows that f of n plus 1 is less than f of n, and therefore that b sub n plus 1 is less than b sub n. To find the limit of b sub n as n goes to infinity, I'll use L'Hopital's rule. The original limit is in the indeterminate form of infinity over infinity. So I take the derivative of the numerator and the derivative of the denominator. And this limit is 0, since the numerator is constant and the denominator increases without bound. So, since both conditions of the AST are satisfied, this series converges. Suppose we want to estimate the sum of a convergent alternating series. Well, we know that a partial sum of any convergent series can be used as an approximation to the total sum, S. And the error of estimation is the remainder. This concept or theorem provides a bound on the error for a series that satisfies the conditions of the alternating series test. The alternating series error bound theorem says that for an alternating series that satisfies the conditions of the AST, the error bound in using the nth partial sum is the positive part of the next term in the series. In words, the alternating series error bound is less than the absolute value of the first omitted term of the series. Here's another example. Consider this alternating series. First, show that this series converges, and then find S sub 6, the sixth partial sum, and use the alternating series error bound to show that this value differs from S, the sum of the series, by less than 1 divided by 150,000. Let's check the conditions for the alternating series test. The positive terms are in fact decreasing. The denominator for b sub n plus 1 is greater than the denominator for b sub n. And the limit as n goes to infinity of b sub n is 0. Therefore, the series converges by the AST. S sub 6, the sixth partial sum, is found by adding the first 6 terms of the series. Here's the analytical answer, which I found using technology, and here's the decimal approximation. The alternating series error bound for S sub 6 is the positive part of the 7th term in the first series, or the absolute value of the first omitted term. Here are my calculations, which show this is less than 1 divided by 150,000. Here's how I used technology to help me with this solution. I defined the nth term of the original series, and I found the symbolic representations of the first 6 terms of this series. Then I found the 6th partial sum, and here's the magnitude of the first omitted term. Here's a graph of the terms of the series and the partial sums. The terms of the series approach 0 very quickly here, so it's a little difficult to see the terms and the partial sums alternating. However, this graph does present some good evidence that the series converges. I hope this video provides some insight into alternating series, a few AP Calculus type problems, and the use of technology to solve and visualize these types of problems. And just a reminder, there are lots of valuable resources on the TI website. There is material there involving technology and calculus, classroom activities, and lots of calculator tips and tricks for test success.